All right, welcome back. So, Phil is going to talk for 1 second about the person pictured in this Wikipedia page, and she has a Wikipedia page, so obviously she's super duper important in the world. And Phil is going to talk about her. You sent a little Piazza post earlier. What would you like to say?
Yeah, so I mentioned earlier in class, I think it was like second lecture, we talked about, I think, fifth lecture about abstract data types, this whole idea we have in software engineering that, hey, you kind of have an abstract interface, and whether you implement it this way or that way is independent of the interface. So Barbara Liskov invented that idea in the 1970s, and she won the Turing Award, the highest award in computing, for doing that, as well as doing all kinds of other things like Byzantine fault tolerance and all kinds of stuff, so she's faculty at MIT. She is a Stanford PhD. She is the first, this says one of the first, but I've always heard first. So we'll just say one of the first women to be granted a PhD in computer science in the United States. And she's actually here today to give a talk at 4 o'clock because she's now a Stanford engineering hero, along with people who, like invented the laser. And Hewlett and Packard and Vint Cerf, the father of the internet, the first woman in space. And so it turns out she had some openings in her schedule, so she's going to be hanging out in my office during my office hours. If you'd like to come chat with one of the greatest systems researchers around, who is totally awesome, then I suggest come by and meet Barbara Liskov. Yeah.
What are your office hours?
When are my office hours?
Yeah.
These things are on the web. Yeah, fair enough. Now I'm curious. You're not asking me on the web, then I get upset. My office hours are 2 to 3 p.m. in Gates 409. Today. 2 to 3 p.m. Gates 409. If lots of people show up, I've arranged another room which is bigger because my office isn't that big. But yeah, so feel free to come by and meet a legend.
Phil's office isn't that big, but it's the nicest office on campus and possibly in the world.
They're renovating Gates, and they started threatening they're going to make me move my office, and I said no.
He won't even let them renovate it. It's got a balcony, so go check it out. Okay, anyway, Barbara Liskov, a giant in the field of computer science. So kind of cool that you might get to meet her today. All right, so let's continue. How's assignment 3 going? I'm hearing a fair amount of people posting things on Piazza. That's good. That's not the slide I want to start on. Not sure why it jumped there. That's the one. There we go. So assignment's going okay? Yeah, if you haven't started it yet, start it soon. It's due Sunday, and there's 4 parts to it. 2 are relatively straightforward. The 3rd and 4th are pretty intense. So get going on that. A week from Monday is the midterm exam. And we'll have more study material out on, I guess, next Monday for the midterm exam. And we will also have one more assignment that is related to the material that's actually going to be on the midterm exam. It will start before the midterm and actually finish after the midterm, but it's not a bad idea to at least get started on the assignment as we go forward. Today, we are starting material that is not going to be on the midterm exam. Well, Phil and I haven't quite discussed that yet, but it, in the past, has not been on midterms at this point. And this first assignment you'll do for the stuff we're going to start today isn't going to be for about a week and a half, 2 weeks, because there's enough to get you, we have to talk about a bunch of things before you're really capable of doing a meaty assignment in it. So we will go forward. What we're going to start today with is we're going to start with another one of these midterm problems from a past midterm. Phil went through one on Monday, and I want to go through a couple more. I just had some feedback that said they were not a bad idea to do this sort of thing so you can think about the types of problems during class. But here it is. Let me bump this up size-wise so you can see it a little better. Here's the problem. It says, consider this program and its execution. Assume all processes run to completion. All system and printf calls succeed. No error checking or craziness going on here. And then all calls to printf are atomic, meaning that they print the entire thing that they should be printing. And let's see, assume nothing about the scheduling or time slice durations. In other words, you can't assume that, I know this process will go before this process. All bets are off unless you have wait PIDs and so forth, in which case then you know that you have to wait for another process. That's the only thing. So the question for this one is list all possible outputs. And what you're going to want to do is you're going to want to go through this thinking about the processes and thinking about what happens at each stage. Once I give you about 6 or 7 minutes to think about it with your neighbor if you want to, we'll come back and then you can ask a bunch of questions about it, and then we'll talk about what the solutions are. Okay, let me make this a little bit bigger so you can see it. Yeah?
Will we share any practice on midterm questions or previous past midterm questions?
This was a previous midterm question, yes. There will be more. Like we'll give you a whole set of a few old midterms to practice from. Yeah.
This should be answered already, but are we on Blue Book for this class, or is it?
I haven't talked to Phil about that yet. That was my plan. We'll see if we're going to be on Blue Book or not. But we'll see. We'll let you know. Other questions before you get going? Okay, give this a shot for about 6, 7, 8 minutes maybe, and think about how you do this. And I'll go through how I would think about it afterwards. And you're really going to need a piece of paper for this. I see some of you trying to do it in your head. Good luck. If you can do it in your head, you're a better person than me. Okay, how are we doing? Are we getting there? I've seen a couple good answers. I've seen some people going, I'm not sure where to start. I've seen some people saying, oh, I kind of get confused in here. That's okay. This is you need some practice on these things when you're doing it. That gets a little bit small. Sorry about that. I think my pen will only work if I do it this thing. Who thinks they have an answer? I've seen a couple good ones. What do you think? Go ahead. 3 answers. Okay. What do you have? 1, 1, 2, 2, 6, 5. 1, 2, 1, 2, 6, 5. 1, 2, 2, 1, 6, 5. I like it. Okay. Very good. Let's talk about how I might think through this. If you didn't get that far, that's okay. All right. Very good. And I saw a few different ones that were the same, and I agree with that. If you disagree, we can talk about it. Here's what I would do. I would start and I'd say, look, there's going to be a parent, and at some point there's going to be more children, and I would probably scan through this and go, what's going to happen? Well, there's going to be a fork in here. The parent is actually going to break, and then the child is going to fork again. So I would probably say, well, there's probably going to be 1, 2 children in here because there's only a counter of 2. So I'd probably start with that, and then I would start filling in some details. And in some sense, it's a little like doing Sudokus where you get to a point and you're like, oh, I don't know enough yet to see what's going to happen. Let me hold for a minute and we'll see. And you end up filling in all the pieces once you analyze the whole program. The next example is going to be even more like that. Here's what I would do. I would say, okay, well, the parent, what's the counter start out at? Well, it starts out at 0 because we have a counter equals 0 here. Okay, sorry, again, that's a little small for way in the back. The counter starts at 0. Okay, and then the parent goes through it. The counter is less than 2, so it forks. But the parent, whose PID, the return value for the PID is going to be greater than 0, immediately breaks. Then you go down here, and the parent says, oh, if the counter is greater than 0, well, it's not. So then it's going to say if PID is greater than 0, it is because it's the PID of the child, so it's got to be greater than 0. So it's going to just wait here, and then what's it going to do? Well, then after it finishes, it's going to increase C to 5, and then print out the 5, right? But we have to say this is after child 1 finishes. So that's the first, I would go through and go, what's the parent doing? That's what the parent's doing. Okay, let's look at child 1. Well, child 1 also starts with counter equals 0. Child 1 goes through, it happens after the fork. The PID is not greater than 0, so it's not going to break, so it is actually going to update the counter to 1 with the plus plus right here. And then it's going to print out the counter. So it's going to be a 1 printing out. Now, there's no real scheduling we know around that 1. It's just at some point it's going to print out. Okay, and then it's going to go and loop again, and then fork again. But this time it's got a PID which is greater than 0 because it's forking and changing the PID to its child. And so it's going to break. The counter is now going to be greater than 0. In this case, it's 1. You're going to get another 1 printing there. And then it says if PID is greater than 0, wait for the child. And let's see, is that going to matter in this case? Yeah, it is. So it's going to increment the counter. In this case, the counter is now going to be plus 5, which is going to be 6, and then it's going to print out 6, but this is going to happen after child 2. And we're getting there on this, right? Okay, the second child, well, let's see what's happening. It's down here. It just got forked, and it just came into existence. Its counter is whatever the counter of its parent is to begin with. That means it starts out at 1. And then it changes it to 2, and then it prints it out. So there's going to be a 2 printed in here. It's going to go down. There's no more looping because the counter only goes up to 2. And then it continues. Its counter is greater than 0, so it's going to print the counter again, which is another 2 is going to get printed. And then the PID for this one is going to be less than 0 in this case, or sorry, equal to 0 because it is a child. And so therefore, it's not going to do anything else. So those are the things that are going to happen in some semblance, some order. Well, the only things that are really going to happen in an order we know, the 6 is going to have to print after the second child finishes. The 5 is going to have to print after the first child finishes. So in the end, we're going to have those print last in that particular order, 6 and then 5. And otherwise, we can have all these other ones in any order we want. So let's start ordering them. We could have 1, 1, 2, 2, and then we would have the 6, 5. Or we could have 1, 2, 1, 2, 6, 5. Or we could have the 2's happen first, 2, 2, 1, 1, 6, 5. And the ordering of the 1's, yeah, that could be changing, but it doesn't matter. You can't tell any change from that. Yeah, question. Does the first one, oh, sorry, sorry, I did get this wrong. You're absolutely right. This one is the one that has to happen before the first child or the second child does anything. You're absolutely right. I screwed that one up. That one has to happen before the second child because it happens before you ever fork. Yeah, they're absolutely right. So I goofed on this one. It is 1, 2, what's the one I missed? 2, 1, 6, 5. That's the other one. Yeah, very good. Thank you. Yep.
Can you explain that one more time?
Yeah, so I when I was going through this right now, I forgot the fact that, or I didn't recognize the fact that the first child has to print before it forks again. So therefore, this 1, the 1 from the first child, is going to absolutely print before anything else. So this first 1 is going to be a fixed 1. These 3 can happen in any order, and then these 2 have to be in the correct order. Yeah.
Is it for this problem particularly, but what if fork returned to 1?
What if fork returned to 1?
Return to -1.
Well, we're not going to worry about that for this one. Yeah, that would be something that doesn't work with the fork, which is odd, first of all, but we're not worrying about that. In fact, we specifically said all system calls succeed. Yeah. Okay, other questions on this part? Does that make sense, that logic of how to go through this? Good. Okay, so that's that one. The next question about this is what happens if we actually change the counter is greater than 0 to the counter is greater than or equal to 0. In other words, what's going to happen if we have this counter or this change right here greater than or equal to 0? Now, I don't want you to write all those out because it turns out there's lots of them. But I want you to think about it for a minute. What would happen if let me leave that up there. What would happen if I kept this up there like that? Or if I changed that to greater than or equal to 0. Yeah.
Well, the first integer would have to print out 0 because it would be the parent and we'll do that.
It could print out 0. Doesn't have to though, but it could, because remember, once you're forking and so forth, things are happening that you can't control when they happen in that case. The only times you can control when things happen are if they happen before you do a fork, which we're not sure about yet, or for this case, or if you've got to wait PID. Those are the only things you can really control in that case. Yeah.
So couldn't you have a 0 anywhere in front of the 6 or no, the 5?
Yeah, good point. Yeah, so let's think about this. That 0 could happen, because it's going to be a 0, right? Because the only time this is going to matter is for the parent, the original parent, is going to get to here, and then it's going to print the counter. In fact, you don't even need the if counter. It's just any time it's going to print the counter there. And so there's going to be a 0 printed. It could happen before the 1. It could happen before the next one. It could happen before the 2. It could happen before the next 2. And it could happen before the 6. It also could even happen before the 5 after everything else happens. You cannot make any assumptions about the scheduling. It could be that the operating system just said, you know what, that parent, I'm just going to push it off the processor until all the other stuff gets done. You have no control over that. And you have no way to predict it in that case. Yeah.
Similar to when we were talking about signals last time.
Yeah.
Is the processor only ever gonna stop your process from running when you go in or out of a system call, or could it just stop
No,
two addition statements?
it could stop it anywhere in your program for any reason, or lots of reasons out of your control. For instance, your program can't run for a very long amount of time before the operating system goes, you know what, you're taking too long, and it just goes, up, a timer's run out, I'm stopping you right here so I can let another process go. That's one reason. Another reason is that it's doing some sort of input-output. So if it's in the middle of like printing, if it's about to print something, it might wait to print that for some other, potential reason. Or if it's reading input, it will certainly wait for something to happen for the input. Lots of different reasons. You don't control any of them as a user program. Yeah.
Why would it print out a 0, or why would it print out a 5 before the 0?
It won't print the 5 before the 0.
Oh.
It's everyone but before the 5.
Yeah.
I mean, it can't do it. So in other words, it can be before the 1 in 1, 2, 3, 4, 5, 6 different positions. Yeah. Meaning that there's 6 times as many different outputs that you could have in that case. So 18 different outputs. Yeah.
What if you call a wait PID on a child that does not exist?
Good question. What if you call a wait PID on a child that does not exist? In fact, that would happen here, wouldn't it? Because in this case, you would get the PID being greater than 0 and waiting on the grandchild. In this case, we do that. It might be that the grandchild has already ended, right? So in that case, it returns -1. The wait PID returns -1.
And would the following code get executed?
And the following code would get executed. It's not an error, it just returns -1 in that case.
So wait PID in this case, so the grandparent is waiting for both the child and the grandchildren?
Well, no, that's a good question. The question was, is the parent waiting for the child and the grandchild? There is no, how should I put this? There is no interaction between a parent and a grandchild at all, really. Once the only thing the parent is going to get feedback on is its immediate children. The grandchildren will report back to their parent, but not the grandparent. So there's no real way to go, oh, I'm going to capture all my children and all their grandchildren as well. Once a process is going, it's going, and the parent has no real control over that. The parent has no control over the grandchildren. Doesn't even know they exist in that sense. Question in the back and then up here. Say again? Wait PID would be -1 if you're waiting on a... Oh. Oh yeah, if you pass the PID -1, it will not clean up after the grandchildren. Just the children. Yeah, good question. Yeah.
So in this case, we're waiting on, so wait PID waits for the process with the number we give it, right?
In this case, wait PID waits on the process on the number we give it because we give it PID right here. Yes.
Because PID is the ID of the child.
In this case, it's the ID of the child because that's what fork returns to you if you're the parent. Okay. Good. Okay. All right. I would term that one a medium challenging problem for the midterm. I would say that's a medium problem. Okay. Other question on that one? Yeah.
How long does that translate to in minutes?
Yeah. I mean, I would probably, if you're taking more than about 10 minutes on this, it's probably, you're starting to push it. But 10 minutes is probably about right during an exam. That's my intuition. Yeah. Do I have other advice for studying for the exam? Yeah, we have lots of advice. We'll have a whole document that kind of lays some of that out. Go over the labs, go over all the code that we've gone over in class, go over your assignments just to kind of, remember what sorts of things we were asking you, and ask questions on Piazza. And then really do the practice exams, so you have those in order. And then we'll go back here. Yeah.
What are examples of conceptual questions that you would also add into a problem like this?
What kind of conceptual question would I add into this problem? Let's see. I might say something like, it might be a question like, what happens if you do wait PID and the child has already ended? Is that okay? What happens if you get to line 12 up here, but the child has already ended? Is that okay? And that's the kind of question I would think would be a good one. Anjali?
Would you,
Say again?
I forgot my question.
Oh, okay. If you think of it, we'll come back. Okay, I want to go through another one. This other one involves signals that are being sent. Okay, this I'll also bump this one up. It says, let's go through another example. Consider the program and its execution. Assume all processes run to completion, all system calls succeed, etc. All printfs are atomic. Don't assume anything about scheduling. Oh, sorry, wrong question. There we go. This is the one. Same exact sort of setup. Fork is not going to fail, all that kind of stuff. Wait PID, the only reason it would ever return -1 is because there aren't any child processes when it returns, etc. Here's the problem here. Okay, and the question is going to be, what is the output? So this problem has one output, as far as I can tell. And it looks like this. A couple things I want you to be careful about, because if you don't get this, you'll mess the whole problem up and then it's not worth it. In here we have a get PPID, which stands for what? Get your parent's PID, so keep that in mind. The second thing that's going to happen in here when you're looking through it, and I'm just presupposing some questions you might have. In here we set up a signal for handler 1. We fork, and then both processes now have that signal handler. Signal 1, they are different, like they're in different address spaces, but they both have that. The child actually sets up another signal handler for handler 2. It replaces the one up here. So that's something that it's just going to do. It's going to say, hey, instead of going to handler 1 when you do, if you see a SIG user 1, do the one I'm now pointing you to here. Other languages do things a little different where they add them together and they happen one after the other. JavaScript's a good example of that. In this case, no. This one replaces whatever signal handler happens to be in existence. Okay? Those are the questions I think you might have off the bat. Try this for about 6 or 7, 8 minutes. See what happens. Oh, sorry. Question is, what's the output of the program? And then what are the two potential outputs if we change a couple things? So I'll leave that all up there for you. Okay. I hear lots of good talking about this one, which means there's a harder problem probably. Okay. Who thinks they know the output? Anybody think they know? Oh boy. Maybe this is, I would term this one to be a hard problem, by the way. Yeah, go ahead. Sure. 110, 1001. I like that. 110, 1001. That should be one after the other. Okay, I like that answer. Very good. You want to see how I might have processed this? Yeah, okay. So again, I'll have to do this kind of small like this. I apologize about that. Okay, again, I would start with the parent and say, what's happening in this parent here? Okay, and in this case, we can look through and we go, there's going to be a parent and only one child, as it turns out. So we've got the parent and the child. Now, there's some global variables here, which are going to maybe throw a wrench into some of this, but we'll see how that manifests itself. Okay, but remember, global variables for the child and the parent are in different address spaces. That's an important consideration here. Okay, so the parent goes through, we get a signal handler. I will say that this is signal handler 1 is what's set up for the parent. Okay, and then that's here. And then it says forks, it's not the child, so it's going to go down here, and it is going to do wait PID until any of the children finish. Well, that means that one of the children, the only child, is going to finish. So then I could say something like after child, we are going to do what? We are going to increment the counter by 1,000. So like counter plus equals 1,000. And then prints out the value. Okay? All right, well, at this point, oh, and by the way, globally speaking, we've got the counter equal to 0, and the same thing for the child, it turns out, when we do that. This is the case where it's like the Sudoku, where you're like, well, I'm not exactly sure what the counter is going to be at this point. It could get changed somewhere else in the program because it's a global variable. So I'm just going to leave it at, like, at some point after C, there's going to be something printed down here that's going to be whatever the counter value is currently plus 1,000. Okay, so I'm going to wait on that. Then I'm going to say, well, that's really all I know at this point about the parent. So let's go to the child. And the child is going to be created in this fork here. At this point, it's got signal handler 1. Okay, it's got signal handler 1. And it also has a counter equal to 0. That's when it starts out. But then it immediately changes the signal handler to signal handler 2. It's whenever we get this sig user called. Okay, so that might be important. All right, and then what does it do? It signals, let's see. It signals the parent with sig user 1. So you go, oh, okay. So the first thing that happens is the parent signal handler gets called. Okay, so this is happening in the child. And you look at what happens there. Go, okay, well, the signal handler that's going to get called in the parent is going to be handler 1. The counter is going to be 0 still. And what's the PID going to be if the parent called fork and then is kind of waiting around? PID in this case is going to be PID of the child. That's an important consideration. Okay, so then we're in here. We're going to increment the counter. This is the parent's counter, so now the counter equals 1. And then we are going to print it. Okay, so we have the first thing that's going to happen. We're going to get a 1. Then it is going to send a signal to whatever PID is. We said that was the child. And so it's going to signal the child with sig user 1, which means then it's going to go and call SH2 in the child, signal handler 2 in the child. Signal handler 2 gets called, and it goes, oh, okay, I'm going to add 10 to the counter that I see. Well, child's counter is 0, so it's going to become 10. Okay, and then it's going to print it out. And then the child is going to exit. When the child exits, nothing else happens. By the way, the child is spinning. I'll show you this down here. The child is just spinning down here, but then it ends. That's the only way it's going to end in this case. It's going to just spin forever unless it gets exited, which happened in the signal handler. So that's that. So it exits. When that happens, the parent, which was waiting around here, it is already exited from its handler 1, and it's just waiting around for the child to end. It ends. Okay, and then it goes down here, adds 1,000 to the counter. Well, in this case, we know the parent's counter is 1, so the counter now equals 1001, and then it prints it out, and we get 1001. That's the only thing that could happen here. Now, what questions do you have about this? Yeah, Lily.
Why does signal both parents get handled first because like in line 17 you can see that it happens first before line 18?
No, it does not necessarily happen before line, 18 happens before line 19. This is 18? Yeah, that will happen before this line, just because that's the way code works, right? Whether the signal handler goes before this, you don't know. Like, you don't know if the signal handler itself is going to get called in the parent yet, but you do know that the next thing the parent does is going to be the signal handler.
Yeah, but like, the thing is you get the signal. So in line 17, what it means is it just replace the previous handler with handler.
Sorry, 17. This will happen before that too. Yeah, in this case it says I'm going to replace my signal handler, in this case the child's, with handler 2.
That doesn't mean it's handler 2 is going to get executed.
No, handler 2 does not get executed here. This is just a function pointer and it is not executed. Signal sets it up so that when the signal comes in, that function will run. That's a critical thing to understand. Yeah, Jose, and then Becca. Yep.
Why even include the spinning line in the first place?
Yeah, good question. Why include the spinning line in the first place? We did. We'll see what happens when we take it out later. But if you want the child to continue for some reason, you might do that. Not a great idea. We learned that last time. The spinning's not great, but that's something that might happen. Sam.
Can you spin without a semicolon in the braces?
In this case, you can't spin without a semicolon because it's a block. Yeah, you can spin like this. C will gladly do that, as it turns out. Yeah.
Can you explain why it's not 1010?
Yeah, well, how could it be 1010? Or do you mean 1011? Yeah, why is it not 1011? And this is to the point about that global variable means something very specific when you have two different processes. What's the idea?
I was going to say that the increment by 10 happens in the child.
Yeah, the increment by 10 is the global variable for the child, not the global variable for the parent. This is critical for processes. Your global variable space is separate for two different processes. This is not going to be the case with threads, which will start in a few minutes. Yeah?
Is it possible for the parent to be, send the signal to the child, still being handler 1, the child exits handler 2, and exits, and so then by the time the parent gets the wait PID, that returns -1, and it doesn't print.
Yeah, this came up, somebody else asked me this. Okay. When does wait PID return -1?
If there's no child.
if there's no children to be cleaned up still, there will be a child that needs to be cleaned up, right? It'll return the PID of any children, like the first child that needs to be cleaned up, whether it's finished or not. It will wait for it to finish if it hasn't finished, but if it has finished, it will still return the PID of the child. Good question. What else? Yeah. Yeah, the question was, could it be that the child exits before you ever get to this wait PID? And the question was, oh, doesn't that mean wait PID returns -1? It turns out it doesn't. It will return the value of the PID for a process that hasn't been cleaned up yet. And the process that hasn't been cleaned up yet is, in this case, the child. So it will still return a value greater than 0. Good question. Yeah.
If you have W no hang, will it return -1 if there's like either no children existing or none that are like currently waiting to be
If you put W no hang here, if at the moment this runs, no children have finished yet, it will return 0. If a child has finished but not yet cleaned up, and this is what's doing the cleaning up, it will return the PID of the child. The only reason it would return -1 is if all the children have finished and they have all been cleaned up. Yeah. Yeah. Wait PID with W no hang as the third parameter will return 0 if there are children still running and they haven't yet finished. It will return -1 if all the children have finished and have been cleaned up. But because this is doing the cleaning up in this case, it will return the actual value, the PID, for the process that it needs to be cleaned up. In other words, the child.
So it will only return the PID of the child if that child is wait PID.
No, well, kind of. I mean, the question was, when will it return -1? If the child ended, all right, before this ever runs, this will still return that child's PID because it needs to clean it up. So that's doing the cleaning up, and then it will do that. The only reason this would never return -1 in our case. The reason is because nothing else is cleaning up for the child process. This is the only place that it could happen. You're never going to get a -1 in that case. Yeah, Sam.
How would you clean up without using wait PID?
You can't.
So wait
Yeah, so the question was, how can you clean up without wait PID? Wait PID is the method we use to clean up the children.
So basically, you're only going to get -1 if you do
You're only going to get -1 if you never fork. Oh, right, in this case, in this program, yeah. Yeah. I mean, if we had a while loop, in other programs we've had while loops where we've called wait PID after we've called wait PID to clean it up. So that's the other situation. Yeah. Way in the back, yeah. Sure.
When there are no more children left to be cleaned up and no more children running, and it's 0 flag, not the no hang flag, then it returns -1?
In both cases, it returns -1. The question was, if there are no more children remaining, and they've all been cleaned up, assume maybe there was some other wait PID or something, this would return -1, no matter if it's no W no hang or not. Yeah. Okay. Yeah.
So does the child actually get the return 0 statement?
Yeah, good question. Does the child ever get to the return statement in the end? Not in this program, it doesn't.
And if you remove the while true?
Yeah, now, if you remove the while true, that's the next part of the question. Like, what's going to happen if we remove that while true? And I'm saying, oh, there's actually 2 different solutions that could happen now. Yeah.
So could you just say like one more time, like in the call, the way we have it set up now with like no W no hang, what are like when does wait PID return like -1, and when does
In this program, wait PID will never return -1 because this is the only place in the program where we're ever attempting to clean up the process. It needs to be the child. It needs to be cleaned up. Therefore, wait PID will clean it up and return the PID of it. That's the case. I know this stuff is confusing.
Oh, so it like just doesn't return if this like.
Oh no, it would return. It just right.
it's
If
not
it's
a
0
child,
here,
it's
it will wait. It will block and not return until that child ends. Good. Yeah. Good follow-on point. Okay. Yeah. Go ahead, Mary.
Is there a collection of questions like this anywhere where we can practice?
Yeah. The practice midterms have questions a lot like this. Yeah. Yeah. I don't know if there's other ones, but that's probably the place you'll get the best ones. Okay. Let's quickly go through this. I do want to get to the threading stuff. If we remove the while true, wouldn't you agree that we still could get the same output as before? Yeah. Because just because this is gone doesn't mean that it has to exit the return from the program otherwise. If this is if there were no while true there, what would this return for the child, Because this is going to run for the child. What's it going to return? -1, because the child has no children of its own. So in this case, the child one would return -1. That's okay. And then it returns 0. So the same situation could happen. But what if it turns out that this does mean that the child ends before the parent actually ever signals it? What could happen? If it's already gone by the time it signals it, could it print its part of the process? No, it's not. Yeah, it's signaling to nothing. There might be an error. It might be a return value of kill would be like -1 or something, saying I couldn't kill that process. It doesn't exist. But it wouldn't stop the parent. So what would print instead if the child ends before any of that happens? Yeah, did I leave it up here? Yeah, it would get 1. The 10 would not print because that would have happened in the child, and then the 1001 would still print. So it would be 1 and then 1001. Yeah.
Why would the 1001 print? Because what if isn't it possible the child finishes and the parent statement it was a child?
Yeah. Okay. This is for the third time. We'll go over this one more time. If the parent gets to this line, the wait PID line, and the child's already done and gone, it still has not been cleaned up yet.
Oh, it hasn't been cleaned up.
So it's going to return the value of the child. So it's still going to go into this no matter what for this particular program. Very good question. For the parent. Okay. Now, if we removed the exit 0, in other words, this, let's say remove the while true and the exit 0, would that change anything anymore? That wouldn't change anything either. You could still have both cases as before. Okay. Yeah, question.
Going back to the removing the while true loop, would it be possible for the signal handler not to run until after 1000 was printed?
Would it be possible for the signal handler not to run until after the 1000 was printed? Not if we removed the while true, you mean?
Yeah.
Well, I don't understand how that could that in this case that would mean that. Sorry, say your question again because I don't think it's actually possible. What's your question again?
Because you're sending the signal to the parent process, right?
You're sending the signal to the parent process.
The the child process could then finish.
Yes, the child process could certainly finish.
Which would then allow the parent process to print 1000. Could that happen before the signal handler the signal is handled?
Could that happen before the signal is handled? No, because if it was already in this about to print that, well, it couldn't be because the child's still going. First of all, so it could never get in there to begin with. Once you get past this signal sending, the next thing in the parent that's going to happen is that signal handler. So it couldn't even have gotten here yet. It's as Phil said, another stack frame is shoved onto the parent, and it's got to go to that signal handler next. Yeah, and then 2 more questions, and then we're gonna. I want to move on to the next thing. Yeah, go ahead.
If you remove exit 0, won't the child just hang?
Yeah, if you remove exit 0, well, if we also remove the while true, then it would be basically the same exact thing. It would return back to here and then do exactly the same thing as before. Nothing else would change. Like, in other words, it would still do the same thing as if we just removed the while true. Nothing else would really change in that case. Yeah? Would it be possible to print, your question is, would it be possible to print the 10 after everything is happening? No, because, again, this has to wait until the child process has ended completely. If the child process hasn't printed 10 yet, it hasn't ended yet. That's happening there. Good. Let's move on to the next. Let's move on to the next stuff. So I want to get to the next stuff so that we can at least introduce this other topic. But you see why that one might be a hard one? That one, there's a lot to it. A lot to that one. Okay. So let's see. We went through all this. I think we still went through. They're all in the slides. All the interesting stuff in the slides is that. Okay. Let's move on to threads. So far, we have talked about processes, okay? And we know that operating systems allow 2 processes to run at the same time. They also allow a process to have multiple, what we call threads of that process running at the same time. Sometimes we call these lightweight processes because the mechanics of them, it does not have to launch a whole new process, which takes time and is memory intensive when things change and so forth. but it's a similar sort of idea. Basically, you're having two parts of your program running concurrently, two or more parts of your program running concurrently. That's what threads will do. In your future programming, the odds that you write programs that use threads is much higher than the odds you run programs that do multiple processes. It's actually much more common to run threads, and we'll see why as we go through this. In this case, your process has a stack, okay, that it comes with, and if we fork another process, it gets its own stack, right? I mean, it has a copy of the original stack, but it gets its own. For threads, the thread manager breaks up that stack into various parts that your different threads can use, which means that your program's threads will share all of the memory. In other words, if you have a value in one function that is a variable on the stack and the function doesn't end, you can then pass that variable, a pointer to that variable, to another thread, and it can act on that. So you've got much more ability to share memory, which means that all of a sudden things like deadlock and race conditions gets amped up a lot more. There's even more chances for race conditions, but that's something we will talk about how to deal with that. Okay. What are some of the good things about threads? Well, it's easier to support communication between threads. They're all in the same memory. You don't have to send signals back and forth. You just update some variables, and you can communicate that way because everything's in the same process space, the memory space. There's no memory protection, though. That's a con. Because you're sharing this virtual address space, you can end up having problems with as I said, more race conditions. It's much easier to do race conditions or deadlock. Okay, you get access to the same globals. Unlike the last problem where we had the parent had different globals, your globals are globals, and if you're a bunch of different threads, they share the same global, which means we have to figure out how to contend for that global without leaving us open to race conditions. Again, okay, and you get a shared stack space, which leads to the similar sorts of issues. Okay, so think about threads as being similar to processes, except you've got much more memory sharing, and you've got other things that, as we'll see, are slightly different. But they're the same basic idea. Okay, you're not launching a whole new process. You're taking your process and kind of making one of your functions or more of your functions run at the same time as the other function in the same process. So that's what's happening there. Okay, turns out C doesn't have native support for threads. In other words, they never built C to support these threads. But most Unix varieties and Linux come with this library called pthreads. And pthreads is a library we'll learn a little bit about today. You've got a data type called a pthread_t, which manages the threads. Okay, you keep track of that when you want to clean up after the threads and so forth. Okay, and the only two functions we're really going to care about in this library, at least for our purposes, are pthread_create and pthread_join. Pthread_create launches the thread, and you basically give it a function pointer, just like we had before, and it runs that function at some point after when you call pthread_create. And then pthread_join is similar to waitPID, where it says, okay, give me a thread ID to join to clean up after, and then it cleans up after it. The difference is that you really don't have an idea of waiting for all your threads like we would have with waitPID. You kind of have to wait for each one individually and join them each of it individually. Let me show you our first threading program. Okay, and let's see, what's this one going to be called? This one is going to be called Introverts. Jerry Kane wrote this program, and he's an introvert, and I happen to be an introvert too, so I can relate to this program. Nothing wrong with being an introvert, just saying that's the way it is. So here's what we're going to do. Okay, let's actually write a function that we want to call in this. We want to call it from our when we launch these various threads. Okay, so what we're going to do is we're going to do this. We're going to just type, in this case, we're just going to type printf I recharge by spending time alone. Okay, like that. Okay, and then in this case, we're going to return null. Now let's look at what the function, the signature of this function is. Should start reminding you of CS 107. There's a void star function with a void star argument. Okay, C does not have any generics that are very easy to use, so you have to deal with it by passing in just a void star pointer, and it's expecting a void star. It's a pointer in return. Okay, so that's that. But that's all that function is going to do. Okay, now in our main function, let's do this. Let's say printf. Let's hear from. We'll use %zu, which is basically because we're using a size. We're going to use a size t here. Introverts. Okay, and in this case, we are going to do k num introverts. Okay, like that. All right, and then let's actually create an array where we're going to keep all of the ID numbers associated with those introverts. Okay, so we're going to have to clean them up later, and we have to keep track of them. It's not like forking where you don't have to. Yeah.
What is thread safety?
Yeah, so good question. Thread safe means that you've got a function which allows you to call it from various different threads, and it's not going to explode. That's really what thread safe means. Some functions are not. Printf happens to be one that is in this case. There are other ones that are not. Good question. Yeah, good question. And you're probably the first person ever to read the comments at the top of this file, so good job. Okay, so what we're going to do is we're going to create a pthread_t array called introverts. Okay, and we're going to create k num introverts number of them. Okay, and that's just an array of those because we're going to keep them in there. Then we're going to do a couple for loops. Size t, I equals 0, I is less than k num introverts, I plus plus. Okay, what we're going to do in here, let me move this down so you can see it a little bit better. Hang on. Move it up a little. There we go. What we're going to do in here is we are going to create them. So pthread create. And we're going to do this. We have to do it this way, where we have to pass in a pointer to introverts, a pointer to the ith value of the introvert. Okay. We also are going to have a parameter that we're not going to worry about, but it basically is there so that if you want to prioritize the threads, you can say, hey, try to make this thread run before this thread. If you want to do that, you can set something there. We're never going to worry about that for this class. And then we are going to pass in the function pointer, recharge. And then we're also going to pass in this case, null again, which would be the parameters for our recharge function. Unlike with signals, for instance, a signal handler, now we can actually pass parameters in to the threads, which is kind of cool. It gives it more things to do. It's got to be a void star pointer, which is kind of ugly, but that's the way it goes. Okay, so we're going to create those. Then all those threads are going to run. Let's clean up after them. For size t, I equals 0, I is less than k, num introverts, I plus plus. And then we are going to join them all. Pthread, EAD, join. And then we're going to have to join introverts I, like that. Okay, and that will join them. And then after we get done, let's do another printf that just says like everyone's recharged. Okay, like that. Okay, so what are we doing? We are creating a bunch of, we've created a recharge function that we're going to call in our thread. We have created an array that's going to hold all those the thread IDs. We've created all the threads, cleaned up all the threads, and then at the end printed everybody's recharged. Question?
Why does pthread create take a pointer to pthread, but
Yeah, so in this case, it's empty right now. So the pthread create is going to populate that variable in our array with the value. So you couldn't do it by just passing the number in, it's because it's a copy in that case. Okay. Yep.
So is the arguments for the recharge has to be void star?
The arguments have to be void star for this function. Now, the good news is next week we're going to start threading in C++, where it gets a little nicer. And a little harder in other ways, but nicer in some ways. Yeah.
What if the recharge function requires more than one argument?
Yeah, good question. If the recharge function requires more than one argument, you pass in a pointer to an array of arguments, and your recharge function needs to figure it out. Just like back in 107 where you went, oh boy, now I have to know the type of the thing that I'm accepting. And it's a little ugly, but it's doable, but it's just a little ugly.
Do you have to pass anything inside of create?
You would have to pass inside of create, you would pass a pointer to some structure that holds all the arguments. You can't pass multiple arguments there.
What happens with the return value of recharge, which in this case, no.
Yeah, the return value of the charge, I believe it comes back in either pthread join or there's another way to capture that. We're not going to worry about it right now.
Pthread join is pretty much like wait.
It's like wait PID. Yep. Yep, in this case. Good. Grace, you had a question? And then back here.
In the slides, pthread join has 2 arguments, but you didn't put it up there. What?
Pthread join has 2 arguments. It does?
So the second one's null.
I'll have to take a look at that. In this case, no, you're absolutely right. It is null. That might be where the return value would end up going. So that might be that I think might be that might be where the return value goes. Good. Thank you for catching that. The compiler might have caught that too. Yeah.
So when does recharge exactly get called? Does it get called instantly when we?
Such a good question. The question was, and this is a great question, when does the actual recharge function start? It is not right here. The thread manager says, okay, I got a thread I have to start. I'm going to start it in my own time. By that time, we're already down to here. Or we're already the next one in the loop. Very good question. It's going to become important in a minute. Anybody else over here? Yeah.
So what happens if you call pthread join before?
If you call pthread join before this will return to you. Pthread create creates a thread ID for you. If you're joining on a pthread that hasn't finished yet, it just blocks. So that's how that goes. Yeah.
Are all threads created started at the same time?
No, all threads are not started at the same time. They're started at some point after you call pthread create.
Like the thread at index that we can start before.
Yeah, sometimes the thread later can start there. I mean, it would be odd that would happen, but it could start then. Yeah, certainly could finish later. Yep.
What's the point of passing the nulls?
You mean like this one?
Yeah.
It's part of the parameters of pthread create. This one is saying I don't have any arguments for the recharge function.
And the one for pthread join?
And the one for pthread join, this one, I believe this, I'd have to look it up, but I believe this one gives you the return value of the recharge function. I think that's what happens, yep.
Could you merge the 2 for loops into one? So like put line 24 right after the
Yeah, good question. Could you merge the 2 for loops into one? No, and you wouldn't retain the same behavior. Because what would happen is it would run the create, and then it would try to join that same one, and it would block. And then when that one finished, it would start the next thread, and then it would finish. We want them all run at the same time. So you couldn't do that in that case. Okay, let's see what happens when we run this. Okay, because we've actually done it. Let's see if I made any mistakes. Make introverts. Okay, good, introverts. And we get, okay, I recharge was saying we get 6 outputs. Everybody's recharged. We could have put the thread numbers in there if we wanted to, and they would happen in any order. They wouldn't be necessarily the same order we launched them in, but that's what's going to happen. Okay, that's our first one. Now, let's look at some of the subtleties about what's happening here. Okay, this is the same program here. You can go run it on your own. Let's see. Okay, we've gone through everything here. We've talked about everything that is happening here. Okay, all right. Once we have some concurrency, then we do have to be a little bit careful. Let me write another program for you. Okay, this one's going to be called Confused Friends. Okay, and I've taken a bunch of names from our class. I've randomized them and taken a bunch of names from our class. You may recognize your name up here. Okay, it doesn't mean you're confused, by the way. It's the way the output happens. You'll see. And then I'm throwing another one on here called an imaginary friend. Okay, so basically I'm creating a list of 6 friends from the class, and then one that I'm just going to call imaginary, just for kicks. Okay, and then I'm going to figure out how many of those friends we are. This is basically just boilerplate stuff that I have to figure this out. We are going to figure out the number of friends by doing size of k friends divided by size of k friends 0. That should look familiar from, actually I'm going to do k friends 0 minus 1 because I don't want the imaginary one to actually be counted. I want the imaginary one to just kind of sit there in the array and not do anything. That's kind of what I want here. Okay, I did this wrong. Hang on. How about that? I think, let's see. Divided by k thread. Yeah, I want minus 1 out here. In other words, yeah, that's what I want there. Okay, thank you for catching that. Okay, and then, so that's leaving out the imaginary friend here. Okay, all right. So then I want to do this meetup function. Okay, and the meetup function is going to be the thing we're going to call from our thread. It's going to be the thread function. Okay, and the thread, this is going to look like this. Const char star name equals k friends size underscore t star args. Oh boy, that's ugly. Welcome to C land. Okay, I am now using an argument. Okay, we're going to pass a pointer in to this function. Okay, we're going to pass a pointer into this function, and then that pointer is going to be a pointer to a string with the name. So we're going to be able to print the name based on this function. Okay. Okay. Actually, sorry, it's not. It's going to be an integer. It's going to be an integer representing the index into the array. That's what it's going to be. Okay. All right. And then we're going to do printf. Hey, I'm so-and-so empowered to meet you. Okay, name. Okay, so there we go. Okay, and then I'm not going to worry about the return value for this. That's that. Okay, so that's all our function is going to do, our meetup function is going to do. Okay, now in main, we're going to have to do some of the same things we did before, where we're going to start all these threads. Okay, so let's do this. Printf, let's here from %zu friends. Okay. All right. K num friends. Okay. And then let's create the array again, like we did before. Pthread underscore t friends and k num friends. Okay. All right. And then we'll do our two for loops for size underscore t I equals 0. I is less than k num friends I plus plus. And then in here we're going to create them all. Pthread create. Okay, and now we have to do something a little different. We're going to say friends I. Okay, that's going to be the get us back the. It's going to get us the thread ID for the thread we're about to create. And then we are going to pass in null for the, we're not worried about the prioritization. We're going to pass in the function we have, and then we have to pass in the argument. Now in this case, let's just pass in the address of the index that we're at. Because we're at index I, let's pass in the address of that index. And when we dereference that address, we will then use it in the array. So far so good. It's going to be a pointer in this case, and that should run just fine. Okay. All right. So we've done that. Then we're going to do the same thing again, and we are going to clean up after ourselves here. Pthread join friends I, and then null. We don't care about the return value. Okay, and then printf something like is everyone accounted for. Okay, and then we return 0. Question, Phil? No? Oh, okay. All right, does anyone see any more bugs in there? Okay, let's try it. Oops, okay. Make confused friends. Okay, confused friends. Hi, I'm Isabel, empowered to meet you. Hi, I'm imaginary, empowered to meet you. And then all the rest of imaginaries. That's a little weird. Let's try running it again. Oh, great, we got some more. Hi, I'm Edward, I'm Jordan, I'm Isabel, I'm Isabel twice. I'm Ann, I'm imaginary. Houston, we have a problem. Right? Something strange is going on here, and it relates exactly back to the question we had a few minutes ago about when this function gets run. Let's look at the code again. what could be the problem here? What could be the problem? What do you think?
You're passing address of I, but I is waiting.
Yeah, look at line 28. I'm passing in the address of I. If we're in a for loop, that I is, the address is probably not going to change, is it? Like it's likely that address is, in fact it won't, the way C works. It's not going to change the address of I, but it will change the value of I. And if I'm passing the address of I in there, by the time the thread library gets around to starting this function, it's going to look at that address, look at that value, get the index out of it, and then go put the index into the array and grab the array. But at that point, the loop has continued and updated I to be the next one, next one, next one, and it leaves I. For loops work this way, where they leave the value as the value after the k num friends value, which in this case points to is the index for the imaginary friend in the loop. Question, Phil.
Yeah, what's especially terrifying about that to me is that when the loop terminates, I is going to pass the end of the array. Right?
Actually, the way we've done this, we've only gone up to k num friends, which is one less than the number in the array.
Right, but I plus put increments and then that.
No, I know. We put an extra friend. We put the imaginary friend into the array. So in other words, we only have 1, 2, 3, 4. We only have, yeah. So I thought about that.
Willie, you're smart.
We thought about that. But it is the case that that variable could be reused. By the way, the compiler could reuse it for something else, and that would be bad. But the point is that we do have to be very careful about what we're passing in, so that the function that gets called, when it gets called, has legitimate data. You have to be very careful about that. Yep.
So we'll always print our friends in order, but it may not print all. It may skip some, and it may print some twice. And
no. So the question was, we're always going to print them in order? Not necessarily. It just will start the first thread probably first, because it's the first one that the thread manager knows about in the loop. So it's probably going to get started first, and then it's probably going to end first. But you can't guarantee those based on the scheduling. But yeah, so there's no real guarantees with the scheduling there either. Yeah. Yep.
So if you start one, then like is the value I already computed when you do your deployment, or is it only good when you get to the line?
Think about what we're. So the question was: is this value when we do this function? We are passing in the address of I, which probably won't change in the loop of the. It almost certainly won't change when you're looping through this. I argue it might change by the time you get to here, because maybe this I is going to start over, and there might be the compiler might be doing something like, I can reuse that space. Probably won't in this case, but it could. But the point is that when the function is when pthread create is called, that value gets passed in, and that's the value that's going to be used. But we've passed in a value that the underlying data changes. That's not what we want.
Yeah, I guess my question is more like you end up dereferencing at a certain point to actually like go indexing to the array.
Yes.
When would that occur?
That would occur when the dereferencing of this value occurs in the meetup function. When the meetup function is running, when it gets to that line, when it gets to line 19, it says, oh, I'm going to dereference it now. At that point, it goes and looks in the value. At that point, the value may not be what we thought it was when the pthread create function was called. Yeah. Good. Okay, yeah.
So would you fix that problem by declaring a new variable?
Yeah, how would we fix this? That's a very good follow-on question. Okay, we're going to fix this by basically doing the same sort of thing, except we're going to now not use something that's going to be changeable, right? Let's actually create a pointer to the into the actual array, instead of creating a value that's indexing into the array. Because once we have the array static, we're not going to change the array. If we could create a pointer into the array and pass that pointer along, everything's fine. Okay, so I've got the same code up here as before. Okay, but now what we're going to do is we are going to change this. We're going to change this in a couple different ways here. Okay, first thing we're going to change is we're going to say, okay, look, instead of indexing into this array, let's just assume in this case that we have a pointer to the array. So instead it's going to be k, it's going to be like this, and the name is just going to be args in this case. Okay? Sorry, it's not going to be, we're not going to dereference it, it's just going to be the actual pointer we pass in. We're going to do that, we're going to pass in a pointer now to the actual constant string inside that array. So that's what we're going to do there. Okay? And then down here, what are we going to do here? We are going to pass in, instead of I, like there's some reference to a value that's going to, the underlying data is going to change. Let's actually pass in, we have to cast it to avoid star, it turns out, but let's pass in k friends bracket I, the pointer to that actual string inside the array. And all of this is allowed because we share the memory, right? So we can actually pass that pointer and it's just fine. That should solve our problem here. Okay? We're passing in the pointer to that value. Let's make friends and see if it works. Friends. Aha. Boom, 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 boom. We don't necessarily get them in the same order, but we get everybody. And it works just fine now. Now we've made it so that what we passed in is perfectly fine. Okay. All right. What questions do you still have about this? Yes.
I'm still confused as to when pthread underscore create spawns off those processes.
Yeah.
It's in a for loop. Are they being spawned off in order, or is it just gonna?
Yeah, good question. So the question is, when are these threads being actually spawned off? Pthread create interfaces with the kernel's thread manager. The thread manager queues these up and then starts launching them when it can. So they will probably be launched in the order that they are put in the for loop here. Whether they finish at the same time is a whole other ball game. They're all running in their own kind of time in some sense, and the scheduler might run them in different places so they end at different times. But yeah, it happens at some point after the fact that you do pthread create, and probably in the order that they are launched in, unless you use this parameter here to say, no, make this one go first, or something like that. You can fool around with that if you want to. Good question. Yeah.
So, looking at someone earlier said was, could you create and assign T within the loop, call it like J or something, set them with the I, and then pass that in and do what you were doing before. I have a feeling that wouldn't work because then you go outside of the scope.
Yeah. So the question, well, let's go look at that other one again. Vim. Confusedfriends.c. The question, and maybe I didn't answer this question correctly, I think you picked up on what the question really was. Could you have said in here something like size t, j equals I, or something like that, and then pass in a reference to that? Probably not, because the way compilers work, it's not going to create a whole new j for each one of the loops. It's going to use the same one again. Yeah. Once the loop ends, you can't refer to anything inside that's still inside that loop. Just, that's because of scoping rules. Yeah. And the stack is what's being controlled here. So yeah, that probably would not work in this case. Good thought. Yeah. And sorry for the person who asked it if I misheard your question. Yeah. Yeah, so this is what Phil was actually bringing up. How did you get to imaginary if you excluded it from the count? I excluded, here's what a for loop works, right? A for loop goes from 0 to k num friends. It counts up, let's say k num friends was 6. It counts up 0, 1, 2, 3, 4, 5. And then it loops again, changes the value to 6, and then checks to see if it's greater than or less than this still. It's not, it jumps out to the end. That's how for loops work. So in a for loop, the last thing that gets set of the for loop counter variable is is the value of the last one plus 1, basically. That's the way C actually does its loops. Good question. Yep.
Could the eyes fall out of scope by the time the for loops end?
Could the eyes fall out of scope? Yeah, that could be a problem too. The eye could actually fall out of scope before the function, and that could be another problem. We didn't see that manifest itself. That could also happen. Yeah. Maybe if we put a sleep in the other one or something and let it go long enough, that variable would be something completely different, and then we'd go off the end of our array and etc. Yeah.
Does pthread join block?
Pthread join does block. Yes, and in fact, I don't know of a way, there's a way to have a thread release itself, basically. We're not going to generally do that in this class, but you can basically say, what is that called? I forget what it's called. But you basically can say, I'm not going to bother cleaning you up. Please handle it yourself. And we're in this case, we're not going to do that. But in general, when we're joining everybody, many times the reason you're doing joins is so that everything can get done before you go on to the next thing. It's a concurrency idea. So you're like, I want all these threads to do their thing, and then I want to know when all of them are done so I can do this other thing. That's generally what we use pthread join for. Somebody had their hand up here, yeah.
So will pthread join, is there any way to know which of the orders that they have come using pthread join?
Correct. You don't know the orders that they're coming in here. You are handling them in the order that you said you're going to handle them in. First one, second one, third one, fourth one.
But then does pthread join have like a return value that you have specified?
Pthread join, I believe it would return the value here, but it doesn't. I don't think pthread join tells you anything about that, because you have to wait for a particular one. You have to give it a thread to join. You have to give it a thread ID to join. So there's no -1 like we had in wait PID, where you can say, give me any one. You just have to join a particular one, which is why we had to keep the array of the pthread IDs so that we could know which ones, what they were to join them later. Yeah, good question. There was one back here and then up here. Nobody? Yeah, no, okay, go ahead.
If you don't call pthread join, could your function just end and then you'll only have run some of the threads?
Yeah, if you don't call pthread join, that's bad. Bad things can happen. Let's see. If we look at friends.c and I get rid of the join, let's see, if I do it this way, and then get rid of the join here, oops, like there. If we run make friends, I'm not sure this will manifest itself, but it may. Friends, let's see. No, it's still working, but it can cause problems with the end of the program. Yeah. What's that? It did work here.
First one, 6 ran, the second one.
Oh, 1, 2, 3, 4, 5, 6, and 1, 2. Oh, yeah. Yeah, you're right. Only 5 ran. So it did manifest. So we had a problem there. We didn't join it, and the program ended, and then that thread kind of disappeared. It got cleaned up before it even ended. Thank you. Yeah. Yeah.
If you call exec VP and like meetup, would that cannibalize the whole thing?
If we called the what?
Exec VP and.
Oh, yeah. Okay, let's talk about this for a second. In general, you have to be very careful about mixing and matching processes and forking and threads. Okay? If you're in a process, you can kind of create as many threads as you want for that process, and things are okay in general. If you fork when there's various threads happening, things could be very bad. If you are in a thread and you call fork, that's probably also okay within some parameters. Later in the course, we'll do a project where you do actually have various threads calling fork, but you have to be very careful about it. So you don't want to do it because they don't mix and match very well. Yep.
Yeah, I mean, so when you fork, you create a deep copy of your process. So you'll copy every thread, right? You're going to copy everything.
Mm-hmm.
If you call exec, though, that's hitting reset. Like all your threads disappear. Everything disappears.
Yeah.
Right. You obliterate the universe and become a new application.
A new application, yeah. So it's you got to be very careful. You have to know what you're doing when you do that. Yep.
So this is kind of that thing, that 5 versus 6 thing.
Uh-huh.
Like, is it possible to have a zombie thread, or once the process ends, are all the threads?
Yeah, I believe, and Phil can correct me if I'm wrong, when a process ends, it kills all its threads. Like if the main fork or threading, the one that called pthread create, all its threads will be kind of canceled, unlike processes which are on their own, independent. Okay, last question if there are any more. All right, we'll see you in lab for next week.